Hi, welcome to Sachin Study Tech. Today topic is asymptotic notations. So here you can see what are the different types of asymptotic notations is there. You can see one by one. So the mathematical way of representing the time complexity. So here representing the time complexity by using these notations. The notation we use to describe the asymptotic running time of an algorithm are defined in terms of functions whose domains are the set of natural numbers. So what is the definition of this asymptotic notation? Definition is asymptotic notation describes the behavior of a function as their input grows large, providing bounds on their growth rate. So that means the growth rate is directly depending on the time plus memory. So what is the asymptotic notation? Why you are using asymptotic notation? If any time complexity can represented by using these notations. Okay, so generally we have the three notations is there. Basically these three notation asymptotic notations are mostly used to represent the time complexity of any algorithm. So those notations are big O notation and big omega notation and theta notations. Generally can use these three notations. Rarely can use the little o notation and little omega notation. So big O notation can represent it, but that is using big O, and big omega notation, this is the symbol, and theta notation and little o notation and little omega notations. Okay, so most of the time you can use the big O notation only, most of the time. So any time complexity, so worst case time complexity can presented by using these big O notations. So these all notation, all five notations is represented in single diagram. You can see here f of n and big O of n and little o of n. Here it is best case, that is the omega and little omega here. So here it can see this is x-axis indicates the input size of the input, and y-axis is indicates the time. Y-axis is indicates the time. Now you can see, for example, you can see some algorithms, the time complexity here in represented in ascending order here. So 1 less than log n less than square root of n less than n less than n log n less than n square less than n cube and so on, and less than 2 power n and so on, less than n factorial less than n power n. So you can see, so any time, any algorithm, the time complexity. So these are the different types of time complexities. For example, you can see here 1 less than log n. Here it can see n, I am considering n is the average key here, average. So less than that n, here it indicates the lower bound, here the lower bound, here greater than that n, that indicates n log n less than n square less than n cube and so on. So here it can represented in upper bound. So here it is upper bound, here left of that n is the lower bound. These are the lower bounds. So these are the upper bounds you can represented. Now you can see in detail one by one, these are the notations. Now the big O notation, asymptotic less than slower rate. Here it is a big O notation is a slower rate. That is the worst time, the worst case time complexity can represented by using big O notation. These notation mostly represent upper bound. So this is the important point, upper bound of an algorithm runtime. Now we can see big O notation is useful to calculate maximum amount of time of a execution. You can see in worst case time complexity represented by using this big O notation. So that is the calculate maximum amount of time. Okay, that particular algorithm takes maximum amount of time. By using big O notation, we have to calculate worst case time complexity. So what is the definition of big O? Now we can see, given two functions f of n and g of n, we say that f of n is the big O of g of n if there exist constants c greater than 0 and n not greater than or equal to 1. That means any input maybe can take at least one input. That's why you can take n not greater than or equal to 1 here, such that f of n less than or equal to c into g of n for all n greater than or equal to n naught. So this is the simple definition. For example, you can see this is the array. This is the array. You can see this is the array consisting of some elements. This is the 4, here it is 2, here it is 1, here it is 5. So these are the 4 elements is there. Okay, for example, if you want to find out key element, the key element is, for example, here key element is 4. So we can compare with all these elements with this key. For example, you can check the first element of that array, it is matching or not. So it is matching, so here it can represented, that is the time complexity is, so that is the best case. So the best case time complexity is omega of n 1. So here it is the represented the best case. So for example, the key is 5, or key is not present. For example, key I am consider key is a 10. So for example, in this case k equal to 5. Okay, that is the key element is found in that array or not. You can see that element is found end of that array. So the time complexity is n. So here this array consisting of n elements, so it is depending on that input. So here it is big of n. So this is the worst case time complexity. More than that it is not possible. So any number of elements you can consider, so that the worst case time complexity is big of n. So for example, k equal to 10, that element is not, for example, not present in that array. Here in that case also you can comparison, and comparison is needed. So that is also a worst case time complexity big of n. So you can represent it by using big O notation in worst case time complexity. Now we can see this is the example. For example, you can consider the two functions f of n equal to 3n plus 2 and g of n value is n. Now we can see f of n less than or equal to c into g of n, is it satisfied or not? You can check it. For example, here f of n is this function 3n plus 2 less than or equal to c into some constant c value, c into g of n is the n. Now we can see 3n plus 2 less than or equal to c into n. Now we can choose any element for c. So I am consider c value is 4. Why I consider the c value is 4? For example, you can consider the c value is 1. Now you can check n value is 1. So that is 3 into 1 plus 2, that is 5 less than or equal to 1 into 1. It always it is not satisfied that equation. So that's why you can take the better, you can take c value is 4 or more than 4. So I am consider the c value is 4 now. C value is 4 and n is 1. For example, n equal to 1. N naught value I am consider here. N is the 1. So here 3n, 3 into 1 plus 2 here, less than or equal to c value is 4 into 1. So here it is not satisfied. The 5 less than or equal to 4, it is not satisfied for n not equal to 1. For example, here I am consider the value is n naught value is 2. I am consider the n naught value is 2. Now we can see 3n. So that is 3 into 2, 6 plus 2, 8. 8 less than or equal to 4 into n naught value is 2. N naught value is 2. So 8 less than or equal to 8. Okay, the condition is satisfied. So here you can check the one more value. N value is 3. Now you can see 3 into 3, that is 9 plus 2. 9 plus 2 less than or equal to c value is 4. 4 into n value is 3. 4 into 3. So here you can see 11 less than or equal to 12. It is also satisfies the equation here. So that's why you can say that f of n is equal to big O of g of n. So you can compare these two functions f of n and g of n. You can see this graph. So here the y-axis is represented the time and x-axis is represented here the input value n. Now we can see the n naught value are find out here. N naught value is 2. Now we can see n naught value is 2. For example, here f of n is the lower bound, f of n is the lower bound, and c into g of n represent the upper bound for all n naught greater than. So here you can see n naught, n greater than n naught. So you can take any value, okay, more than that 2. So it is it satisfies that equation f of, you can represented f of n equal to big of g of n. Okay, thank you for watching this video.